Good afternoon. My name is Stefano Facchini, and today I will be presenting my master's thesis, whose title is Fuel Consumption Prediction in the Airline Industry. This is the final project for my master's degree offered by EIT Digital as part of their master school, and where I had the chance to spend my entry year at the University of Twente in the Netherlands and my exit year at Aalto University in Finland. This project was carried out at Finnair under the supervision of Professor Alexander Jung and the guidance of my company advisor, Mr. Bertan Juhas. The document is structured into 5 chapters. We start with the description of the problem, where we describe what challenge we're going to tackle. Then we move toward the literature review, where we describe what is the current state of the art and we see what is the current status of the research. On the third chapter, we go through the implementation phase and we describe which models we will be implementing. In the fourth chapter, we evaluate those models, describing the metrics and the results that we achieved. While in the chapter 5th, which is the last one, we describe our conclusions and what are possible future steps. And of course, before everything else, we state which is the problem that we want to solve and what are the motivations that move us toward the success in this research. So what is the problem that we want to solve? We want to be able to quantify, to give an idea of how much fuel will be consumed by future flights, and how it can be done now. It is based on historical data, but this is quite limited because you can only be limited to scenarios that were seen in the past. So we want to extend this capability to also try to forecast new scenarios and also to include more detailed data for each flight. This can be done with machine learning models, but of course there are many options out there. There are many different machine learning models, and there is no way to know beforehand which one is the best. So what we are gonna do, we are just gonna implement many and then compare the performances based on some metrics that we will define later, and compare those metrics to understand which one performs better. And what are the motivations that move us toward the success in this research is that we want, first of all, of course, to improve the accuracy for future cost forecast, because once you have an accurate prediction for how much fuel you're going to consume, then you can also understand how much it will cost you. We also want to integrate more low-level data into our model, so that not only you have from where to where you fly, but also, for instance, how many passengers are on the plane, or how the weather is going to be, or other features that we will see later. And finally, also to forecast new scenarios, namely unseen aircraft origin destination combinations, but also, for instance, when current conditions change, such as you want to fly a new route with a different aircraft, you want to estimate how much it's going to cost to you. Or for instance, with the current conflict between Russia and Ukraine, you can still, for instance, fly from Helsinki to Tokyo, but you can no longer fly above the Russian airspace. So you have to take a different route, the distance is going to increase, and we want to also include those details in the model to tell you what is the new fuel consumption. So we started by giving a look on a more general level, how performance were assessed in classic vehicles, so not only on aircraft, but for instance also on cars and motorcycles, where tests are executed in laboratories or other dedicated spaces, not only as a vehicle itself, but also the single components were tested to describe their efficiency, their performances. And then after that also different datasets were released under a variety of licenses. And while moving back to aircraft instead, the same kind of tests were not possible, of course, due to the size of the components. So most of the performances were described by mathematical models, and they were, of course, related to specific aircraft type. But how these cost analysis and performance analysis were done was mostly based on historical data. And so looking at history, you can see how it is going to perform for your next flight, for instance. So the focus of our thesis is to implement a machine learning model or more machine learning models whose aim is to describe how much fuel a certain flight is going to consume. And we can see that this is a regression problem because we will see that our input data are of mixed kind, so that we will have some categorical values and some continuous values, and our output, our prediction will be a continuous value from 0 to few thousands. The data that is available to us can be split into two categories. The first one is the properties of the aircraft, and the second one is flight-related variables. The first one is all the constant that belongs to a specific airplane, such as a brand, the model of the aircraft, and few other values such as center of gravity, drag coefficient, and all those values that are specific to that model in particular. While the second group is flight-related data and is specific to a flight, so from where to where you fly, how many passengers, how the weather is going to be, how long the flight is going to be in hours and minutes, and those kind of variables like that one. And since we can't know which machine learning model will work the best before the implementation phase, we proceeded to implement a variety of them, which can be split in standalone models and ensemble methods. Standalone models are the most traditional ones, the most simple ones, such as linear regression, decision tree, neural networks, which consist of one single model that does the training phase and the prediction, so that the result of this model will be the outcome of the prediction. While the second group, the ensemble methods models, are take it one step further. So they are a group of weak learners, such as a group of, for instance, decision trees, and they are all trained individually, and they all comes up with a result, and then the results are averaged out, and this average would be the result of your model. And before starting with the implementation, of course, we have to go through some important steps of the pre-processing and data cleaning. The most important maybe here are the check for missing values that can really degrade your results. Then the encoding of the categorical data to make those values understandable by machine learning models. And the feature rescaling, for instance, the wind value went originally from -60 to 60, and it has been rescaled in our project from -1 to 1. So we start by describing which are the models that we implemented. And the first one, or actually the first two, are linear regression models. The first one is a simple linear regression. As it can be seen in the example picture, is a regression that tries to fit a line among all the data points, trying to minimize the margin among those points. But this can only work with one explanatory variable. So we take this one step further, so to multi-dimension, implementing this multiple linear regression that can fit a line that minimize the margin among those many dimensional. And of course, this then can go from n variables to 1. Then we try to implement few neural networks where our variables were working as input and our output node will give the prediction. We both tried with 1 and 2 hidden layers and with variable size of number of neurons per layer. And those models, consist of weighted nodes, which each node has a weight, which is a continuous value. And this model can be seen as a black box because it's very complex and it has low explainability. Another standalone model that we implemented is support vector machine, or SVM, that can be used for both regression and classification. In our case, of course, we use it for regression, and it works by finding the hyperplane that has maximum margin between the data points, and it applies a kernel function to split the data that will be non-separable in the current dimensionality. So first it applies a function and to find a way that those different points are separable, and then find the hyperplane that fits into this gap. And the last standalone model that we implemented are decision trees, which are a flowchart-like structure where each node is a decision or a set of decisions. And you start from the root node, which is, for instance, the picture is the top one. And based on the path that you take, you reach a leaf which will contain an outcome. While for the sample method models, instead of having only one model that does the job, several models, several weak learners are built, and usually those are decision tree, but it's not really binding. And you just train several models individually, independently, one from each other, and then you take their outcomes and you average those, and the average of this will be the decision of your ensemble method. For instance, the models that we implement here are random forest, adaptive boosting, and gradient boosting, which are all based on decision trees, but the difference relies on how those different individual decision trees are built. And for the actual implementation phase, we, after performing some feature selection and encoding of categorical features, we end up with 14 input features and of course one output feature, which is our target variable, and around 80,000 lines, 80,000 records. So finally, our data set is going to be 80,000 rows by 15 columns. And the error metric that we will use to evaluate our models are 4. So the root mean square error, mean absolute error, mean absolute percentage error, and R-squared value. Those 4 are very popular metrics, but we can see that highlighted there is mean absolute percentage error because our output feature vary from a few thousands to around 50 or 60,000, depending on the row, depending on the record on the flown distance. So this is the range, and having a percentage will help us in normalizing the error on the scale that we are gonna measure it against. Because of course an error of 5,000 on 10,000 is way more significant than an error of 5,000 on 60,000. And regarding hyperparameter tuning, we saw that many models that we implemented allow for hyperparameter tuning, whether this is done manually or by algorithm. And some values that we change are, for instance, learning rate, the depth of the decision tree, some parameter such as gamma and epsilon in other models. And we can see, for instance, in the picture, how the uh, MAE error changes the maximum depth in decision trees. So this is quite significant and an important step. And while gathering the results, we'll also compute the mean absolute percentage error, which is our designated metric on the test set, so that we will be able to check for bias and overfitting if the mappe on the train and the test set is very different. We will be able to draw some conclusion from that. And also we will be comparing the results only of the best version of each model. This means that for each model where we perform hyperparameter tuning, we will only be keeping the best version based on the mappe metric. For instance, in the decision tree, we see that we tried with different maximum depth of 5, 7, 10, 12, 15, up to 20. And we will be keeping the one with 10. So for the future, we discarded the other ones, and we will be comparing the one with maximum depth set as 10. So after running the test on all of our models, we put the results together in this table, and we keep in mind that we will use the mappe matrix as our designated error measure. So we proceed to sort these results by this. We see that the random forest has the best performances, followed by decision trees, while the worst results are achieved by SVM. And we keep in mind that we also gathered our metric on the test set in order to understand if there is any overfitting in our model. But we can see here that our mappe on in our models is quite similar between the train and the test set. So we can say that this is not the case. So the overfitting is not so present in our project. And another metric that is said to be among one of the best ones to assess performances is the R-squared metric. But we discussed that this is not so useful in our case because we achieve a value close to 1 in all of our models. So this adds no valuable information to our conclusion as it can be seen in this plot. And after we finally identify our best models, which we said are random forest and decision tree with mappe values of 5% and 6%, we can also draw some future steps and future development that our research might take on, which is the integration of additional data to aim to reduce our inaccuracy even more, to try different and even more complex models, other models and other ensemble methods to try to compare their performances. And another possible step might be to include analysis of the cost per liter of fuel, so that not only we can understand how much fuel is consumed, but how much it will cost for us to use that amount of fuel. And this was everything for the presentation. The results will also be presented internally to discuss possible implementations and future direction to take on with this project. Thank you for following, and have a wonderful day.